In this lesson, we're going to start introducing some derivative rules, beginning with some basic ones that we can use to build up others that we will eventually start using. We'll begin by looking at derivatives of constant and linear functions, and then we'll turn to how to apply the derivative operation to sums, differences, and constant multiples of functions. Let's begin with derivatives of constant and linear functions. So we're embarking on a study of derivative rules, and you can think of these as formulas that will allow us to find derivatives of most of the common functions that we study and use all over the place. And by the end of all of this, we will have rules for the derivatives of all sorts of functions: constant functions, linear functions, polynomial functions, rational functions, radical functions, trigonometric functions, inverse trigonometric functions, exponential functions, logarithmic functions, and compositions of functions. That's a long list, and it will take a while to establish formulas for derivatives of all of these different kinds of functions. We'll begin with some fairly basic rules for derivatives of constant and linear functions, and how to find derivatives of arithmetic combinations of those and other types of functions. For the constant rule for derivatives, we can kind of begin by predicting what it should say. This is going to allow us to find derivatives of constant functions in a single step. And if we look at the graph of a constant function, we can predict what the derivative rule or formula for a constant function should tell us. Take a constant function of the form f of x equals b, where b is some fixed constant like 4 or 10 or -3 or anything like that. The graph of such a function is always a horizontal line going through all the points where y equals b. So it looks like what we see there. Again, that's a horizontal line, and horizontal lines have slopes of 0. So we might predict that the derivative rule for constant functions tells us that the derivative of a constant function is 0. Let's see if that's how things come out. We're going to derive the constant rule for derivatives by using the definition of a derivative. So let's take our constant function f of x equals b and put it into one of our derivative definitions. We'll use the first definition that we introduced in our study of derivatives. So the derivative f prime of x for our constant function will be this limit. And here, both f of x plus h and f of x are equal to b, because f of x is equal to b for any value of x. So in the numerator, we just have b minus b. That simplifies to 0. And so we're taking the limit as h approaches 0 of the constant 0. And since the limit of any constant is just that constant value, that limit is equal to 0. So this confirms what we predicted. The derivative of any constant function is the constantly 0 function. We can do something similar with when it comes to a formula for the derivative of any linear function, not just a constant linear function. What we can do to start is to recall that a derivative gives us the slope of the graph of a function at a particular point. So if we have a linear function, we can express it using an expression of the form mx plus b, where m and b here are both constants, and in particular, the slope of the line is m. So we should expect that the derivative function should be m, because that will give us the slope of the graph of f. Let's see if that's how things come up if we apply the definition of a derivative. So let's let f of x be mx plus b for some constants m and b. This time we're going to use our second derivative definition. It just makes the algebra involved a little bit easier. So we're going to find the limit as x approaches a of f of x minus f of a over x minus a. And we're letting a here be arbitrary. We're not assigning it any particular value. So this will give us the value of f prime of a for any value of a, which will in effect give us the derivative function for f. f of x is mx plus b, and so f of a is ma plus b. So we can substitute those into our limit. With a little bit of simplifying, we get mx minus ma in the numerator, and we can factor out a common factor of m. That allows us to cancel the common factor of x minus a, and we're left with the limit as x approaches a of m, where m is a constant, and recall again that the limit of any constant is that constant. So that limit is equal to m, which means that the derivative f prime of a is also equal to m, just like we predicted. So those are two basic derivative formulas for constant and linear functions. Let's include now derivative formulas for sums, differences, and constant multiples of functions. This is going to take a little bit more setup. What we're calling our derivative rules are types of formulas. They're formulas that give us the derivative of a function if we, in effect, plug in the function we're working with. So, like any formula, these derivative formulas or derivative rules need to include variables. But there's an important difference here between these formulas and the formulas you're familiar with from, say, algebra or maybe physics or something like that. In our derivative formulas, the variables that appear will typically be function variables. In other words, there'll be symbols that need to be replaced with function expressions. So to understand what that means, contrast this with a familiar formula, it's like the quadratic formula. There you see it, right? This is the formula we can use to solve quadratic equations by using the coefficients of the quadratic polynomial that appears in them. And here, when we're using this formula, we assign numerical values to a, b, and c. These are, in other words, what are called number variables. They represent numbers. In our derivative formulas, we're going to have variables that represent functions, not individual numbers. Now, we didn't need these in stating the constant and linear function rules that we derived a moment ago, because those kinds of functions have standard algebraic representations. Any constant function can be represented by some arbitrary constant, we use b, and any linear function can be represented by an expression of the form mx plus b. But our other derivative rules will be applicable to functions of any form. And so here we will need variables that can stand in for any function whatsoever. So let's lay down some conventions for these variables. We'll use, as usual, letters from the alphabet to play this role. And as we often do in other contexts in math, we will choose certain standard letters to use for this, to do this job. And these will be our default letters to serve as function variables if we don't have a good reason to use something else. And the letters we'll reserve for this are U, V, and W. Typically, when you see these, they're standing in for functions, but we typically won't write things like U of X. We might occasionally, but we often want to avoid that because we want these letters to stand for any function whatsoever, not just a function whose independent variable is X or any other particular numerical variable. So we'll usually just stay with U, V, and W. So what this means is that if you see U, V, or W appearing in a calculus context, you can probably assume that that letter is standing in for a function. The one exception to this is if you see the letter V being used to represent a moving object's velocity. And in those cases, the context will make very clear that V is playing the role of velocity instead of a general function variable. With that little preamble about function variables out of the way, we can state the sum rule for derivatives. So this rule tells us how to find the derivative of a sum of two functions. And here are our function variable letters appearing. We'll call these functions U and V. And the rule, fortunately, works pretty much like you would expect. Here's a statement of it. On the left side here, we're taking the derivative d dx of the sum u plus v. On the right, we have du dx plus dv dx. So what this means is that if you want to find the derivative of a sum, start by finding the derivative of each part separately and then add the derivatives together. Let's take a look at an example of the sum rule in use, and then we'll look at a proof of it. We're going to find the derivative of this function here, x squared plus 3x. To do this, we'll need to recall something that we came up with earlier using the definition of a derivative. We saw a while ago that the derivative of x squared is 2x. So let's take that for granted. With that, and some of our derivative rules that we've introduced, we can find f prime of x here. So we're trying to find the derivative of x squared plus 3x. And the sum rule tells us that we can break that apart into a sum of two separate derivatives, the derivative of x squared and the derivative of 3x. We know that the derivative of x squared is 2x. To deal with 3x, so by the way, this was justified by the fact that we know the derivative of x squared. To find the derivative of 3x, note that 3x defines a linear function. So its derivative will be its constant slope, 3. So here we're using our linear function rule for derivatives to find the derivative of 3x. And now we're done. The derivative of x squared plus 3x is the function 2x plus 3. To see why the sum rule is true, let's apply our definition of a derivative. We're going to use along the way here, by the way, what's called the sum rule for limits. We introduced this when we were studying limits, and it says, in effect, that the limit of a sum is equivalent to the sum of the component limits. So let's apply the definition of a derivative to the function u plus v. The derivative of u plus v will then be the limit as h approaches 0 of what you see here, u of x plus h plus v of x plus h. That's our function u plus v evaluated at x plus h, minus u of x plus v of x, which is our function evaluated at x. That all gets divided by h as part of the definition. And we can split this into, or we can rearrange the numerator rather, so that all of the u values are grouped together and all of the v values are grouped together. This is just using the associative and commutative properties for addition. We can then break this into two separate fractions. One in which the u parts appear in the numerator, one in which the v parts appear in the numerator, and the denominator in both cases is h. And now we're taking a limit of a sum. So the sum rule for limits says you can separate that into two different limits and then add those together. And now notice the limit on the left is du dx, the derivative of u. That's just applying the definition of a derivative. And the second limit after the plus sign is dv dx, the derivative of v. That proves the sum rule. It shows that the derivative of u plus v is the derivative of u plus the derivative of v. The difference and constant multiple rules for derivatives are similar. One of them allows us to find derivatives of differences of functions. The other allows us to find derivatives of constant multiples of functions. Here's the difference rule. It looks a lot like the sum rule, except instead of a plus sign joining our function variables, we have a minus sign. And the constant multiple rule allows us to find the derivative of any constant multiple of a function. So here c is a numerical constant, any one that you want. The constant multiple rule says that if you want the derivative of c times your function u, take the derivative of u and multiply it by c as well. Notice that we don't use the derivative of c here. The derivative of c, which is a constant, would be 0 for any value of c. And that would mean that every function has a derivative of 0. So if you prove the constant multiple rule, you see that you don't end up using the derivative of c in it. You only use the derivative of the function u. So let's look at an example involving the difference in constant multiple rules, that should say. We'll find g prime of 4, given this definition of g of x, negative x minus 3 times the square root of x. One thing we're going to need to use here is the derivative of the square root of x. We found this a while ago. Using the definition of a derivative, it is 1 over 2 times the square root of x. So g prime of x, by the difference rule, will be the derivative of negative x minus the derivative of 3 times the square root of x. Since we're taking a derivative of a difference function, we can take the derivative of each part and then subtract in the same order. So there we're applying the difference rule for derivatives. The derivative of negative x is negative 1. That comes from the linear function rule. Negative x defines a linear function with a slope of negative 1, so its derivative is negative 1. To deal with the second part of that, the derivative with respect to x of 3 times the square root of x, notice that 3 there is a constant multiple. It can be brought out of the derivative. That's what the constant multiple rule allows us to do. And we already know then the derivative of the square root of x, it's 1 over 2 times the square root of x. So that's using the derivative of the square root of x that we came up with some time ago. And now we're effectively done. You might do a little bit of algebraic cleanup, but that gives us our derivative function g prime of x given this definition of g of x. Now our goal here is to find g prime of 4. At this point, all we need to do is to plug 4 into that derivative function. This is what we get. And with a little bit of arithmetic, you can calculate the value of that to be negative 7 over 4. That is the value of g prime of 4. A moment ago, we proved the sum rule, and we saw how it can be obtained from the definition of a derivative. As an optional exercise, which we will not do here, you might try proving the constant multiple and difference rules. We won't do this here just for the sake of time, but you might try it as practice. It's a good way to get some practice using function variables and applying the definition of a derivative. The proofs are very similar to the proof of the sum rule and use some limit principles that we introduced a while ago. So if you're trying to do this and you get stuck, you might go back and take a look at that proof we gave of the sum rule to see how you might modify it for the difference rule and the constant multiple rule. In all of these cases, the key is to use relevant limit rules. For the difference rule for derivatives, you'll use rules for limits of differences. And for the constant multiple rule, you'll use limit rules involving products.